Hello and welcome to Open Logic. In this video, we are going to look at the general read and write operation of a DDR channel. Before we start, you should know that the description in this video is not accurate, because to make an accurate description, we have to look into each specific technology like DDR4, DDR5, LPDDR4 or LPDDR5. We may do so in the future, but in this video, the description is generic to all and it would be closest to LPDDR4. First, let's start with a Non DDR protocol. These are the common signals used to access a memory. There is a clock or write signal, an address bus, and a write data bus for writing. And for reading, there is a read signal and a read data bus. Now to perform a write, we assert the write signal and we provide an address and a write data. Most of the time, these three signals are provided at the same clock. And to perform a read, we assert the read signal and we provide an address, and the memory will return the data later. The data can be returned at a fixed timing. It can be fixed at the next clock cycle, or it can be fixed at 2 clocks later. The data receiver will need to know this timing in order to be able to sample correctly. However, some memory can return the data flexibly at any point of time. In those cases, the memory will have an extra signal, data valid, to indicate the return of a read data. There you go, this is a simple interface and a simple protocol for accessing a memory. Now let's take a look at a DDR channel. First thing first, a DDR channel is not a DIMM. We will revisit this later. A DDR channel uses a pair of differential signals as command clocks. Generally, differential signals has better signal integrity and can run faster. The suffix T represents the true or positive clock, and the suffix C represents the complementary or negative clock. Next, a DDR channel has a chip select bus CS, which is used to select a rank. If a channel supports 4 ranks, it would have 4 CS bits. Although rank is part of an address, it is handled differently because of how DIMM and memory slots are used. Imagine you have a channel with 2 memory slots that can support 4 ranks. You can insert 1 DIMM of single rank, or you can insert 2 DIMMs of single rank, or you can insert 2 DIMMs of dual ranks. If a rank is treated as an address, there would be 2 bits for chip select, and the DIMM will have to decode if an instruction is meant for them. But DIMM doesn't have a decoder. If you purchase a DIMM, you can insert it at any memory slot. A DIMM is unaware of which rank it is assigned, and therefore it only makes sense that every rank has a dedicated chip select signal. Next, DDR channel has a command address bus CA. It is equivalent to the write signal, the read signal, and the address bus combined. Now specifically for DDR channel, there is a data clock or a data strobe DQS. It is also a pair of differential signals, and it is clocking for data transmission. As compared to this one, a DDR channel has separate clocks for command and data. And finally, there is a data bus called DQ. Now these few signals are called DQ and DQS because in digital logic, a flip-flop input-output is usually labeled as D and Q. Note that both DQS and DQ are bidirectional. The DQ is used for both write data and read data. Now let's look at the protocol of these signals. For the command clocks, the 2 clocks are 180 degrees out of phase. For chip select, it is a critical control signal. It has to be driven to a known value. On the other hand, command address CA can be driven to high impedance when it is not in use. Now, CS is a bus, but to make it easier to visualize, we will only look into CS0 in this diagram. You can imagine that the other ranks are not in use. In order to send a command, we need to assert the CS signal together, else the command is not taken into account. A DRAM command generally requires 2 cycles. You must assert CS at the first cycle, but it's not necessary for the second cycle. But you can assert it nevertheless, it's just that it's not a requirement generally. Depending on the technology and the command type, some commands require 4 cycles, and you may see something like this. We'll discuss more about this in future video. Now let's say we are sending a write command. The DQS and the DQ may be in high impedance at first for saving power, so we need to kickstart the DQS. Once the DQS are stable, we can send the data through DQ. For DDR, data are sent in burst mode, meaning that if we send an instruction to write to address 0, we are actually writing to address 0, 1, 2, 3, and so on. Common burst length is 16 and 32, but we are showing a burst length of 8 here for illustration purpose. The reading from a DDR channel is pretty much the same, except that DRAM transmits the DQS and DQ. We initiate a read command by asserting CS and CA together. After a while, DDR will kickstart DQS, and once they are stable, DDR will transmit the data over DQ bus. Now let's pick some brains on this protocol. In this diagram, DQS has the same frequency as CK. This is true for DDR4, DDR5, and LPDDR4. But regardless of the technology, if DQS and CK has the same frequency, why don't we just use CK as the data clock? Why create extra signals, especially if it's expensive? This is mostly because of delay impact on high-speed operation. Imagine if we have a controller and a DRAM. The controller provides the clock and the data bus is bidirectional. Say the controller sends the write data, the DRAM would receive the clock and write data. Even though both sides look the same, there is a difference. In absolute time, DRAM would see the signals later due to propagation delay. But it doesn't matter because the relative timing between the clock and the data is the same. However, when we are doing a read, the controller sends the clock, the DRAM receives the clock and returns the data. In absolute time, we can see that the data received at the controller side would be delayed. In fact, the data could land on the negative side of the clock. This would make read data sampling a lot harder. As such, whichever side is responsible of sending the data, it should be responsible of sending the clock as well. Since we need the data clock to be bidirectional, it has to be separated from command clock. Next, this delay from when a command is issued until when a data is seen, this is known as latency. If we are doing a write, this is write latency, and if we are doing a read, this is read latency. Let's focus on write latency. When we want to perform a write, can we kickstart the DQS at the same time and send the data at the same time? Or must we wait for the latency? The answer is we have to follow the latency. If we look at the operation at a bank level, to access a particular location, say address 0, the whole row is activated and loaded onto the sense amplifier. This process takes a lot of time, and you have to do it to every bank on every chip in the same rank. So when we send the write command, we wait for this process, then we send the data during the correct window. Reading is similar. There is no handshake signal to detect when a valid data is on the DQ bus, so we need to sample the data at the correct window. And now this is possibly the most interesting and also the most challenging aspect of DDR operation. Say if you want to send two write commands, can you send it this way? You should know by now that you cannot because every command must obey the latency restriction. For the second command, we can imagine the data to start here, and if we backtrack the latency, the second command should start here, and therefore, generally, from one command to another, there is a delay requirement. Now, what's even more interesting, different kind of command has different delay. As a simple example, if the next command is writing to a different row, the delay is different as compared to if the next command is writing to the same row, because the row is already activated. At the end of the day, the controller needs to know the timing very well. The time when to send the next command, and sometimes the type of the next command depends on what the current command is. And this is on top of the requirement where we need to constantly send refresh command to idling data on other rows. Well, that's it for this time. Thanks for watching, and as usual, do help to share, like and subscribe.